il y a le réseau amateur et il y a aussi des gens qui sont très intéressés par l'acquisition du matériel. Et ça serait bien que j'espère qu'on aura l'occasion, de... Je vous remercie. Donc, je te remercie, François, et go ahead. Thank you very much. Oui,
merci. Oui.
Juste au niveau du déroulement, donc you can ask your question during the course. Okay? Go ahead, thank you.
Merci beaucoup, Abdelmajid. So thank you very much. Hello to everybody. I hope that you can hear me correctly. And well, like you said, what you said is perfect. I am. My background is I'm a mechanical engineer, but I am an amateur astronomer for a long time, and we have developed some instruments, and we have even created the company Sheliak Instrument in 2006, if I remember properly. And then I've been lucky to be involved in the development of several instruments in Sheliak, like the LARES-3, the LISA, the LP600, and also the E-shell. So you have an E-shell, and I'll take some time to talk about your E-shell during my presentation. And well, I'm also one of the organizers of the OHP meeting, OHP Spectroscopy party. The OHP is the Observatoire de Haute-Provence in France. And every year we have a meeting where we had the opportunity to meet with Abdelmajid and Zouher. So that's a great place, and this is great to have the opportunity to meet you. Well, maybe I will share my screen to start with my presentation. And what I propose, if you agree, is that I'll start with a quick introduction that I'm doing right now, and then I will talk about the spectroscope itself. Really, I will focus on the instrument and how to use it. My understanding is that you had a lot of presentations talking about astrophysics, which is perfect because this is the most important, in fact. But I will focus on the instrument itself and how it works and how to use it properly. And we look at the main parameters for this instrument. If you have to choose one or to tune one, why not your instrument? And I will also give you some recommendations when you're observing in the field for real. I think there are some key elements that are important to understand when you're observing. And then for me, we'll have some discussion at the end, if you want, of course. And well, as Abdelmajid just said, don't hesitate to interrupt me, to ask questions when I talk. So I don't know how it will it will work regarding the sound. I'm not sure to hear you, but the idea is really you can interrupt me, you can ask questions when something is not clear. I think it's much more interesting for everybody. It is more reactive and more in real time. So don't hesitate. Okay. So who I am, I've also already told you that. I think I didn't forget many important things. And now I'd like to talk about what I call the astrophysics triangle. And well, Abdelmajid or Zouher, is it okay? Well, maybe this is where you are the chairman for the talk. Is it okay for the agenda? Can you hear me properly and so on?
Impeccable, super, merci.
Perfect. Okay, so I go ahead. Okay, so I like this graph that shows that when we're doing astrophysics, but it is probably much more general, and when we are doing science, we always have to switch between the theories, the instruments, and the observations. And for me, this is really important to understand that. So these three actors or three domains are necessary to do science. And you need to have theories and models of the universe or the stars or the galaxies or things like that when you work on it. But you also need to have some instruments. And in astrophysics, you know that there is a lot of technicians and engineers working to develop new instruments or new technology, like the fiber optics, for instance, or the CCD camera, which are very important to make new steps in science. And you also have people observing for real, using the instrument and comparing the results of their observation with the theories made by the theoreticians. Okay, and this is important that to understand that when we are doing spectroscopy and astrophysics or spectroscopy for astrophysics, we really have to take care of the three domains. And this is something which is very interesting, well, especially for the amateurs. You told me that there are some amateurs online. This is something very interesting for amateurs because you have to understand at least a little bit in these three domains, you know. And so you have to understand a little bit about astrophysics. You have to understand how works the instrument to understand where our measures come from. And you also need to understand what are the constraints in the field when you are observing for real, to also understand what kind of measure you can be. Okay. During my talk today, I will really focus on this part. So I will be mainly focused on the instruments. And I'll take time to describe in detail how works a spectroscope. But I will also talk a little bit about the observations at the end of my presentation. And I will not talk about astrophysics and theory, and well, probably because I would not be able to do it seriously, but also because I've seen that in your program you already have a lot of presentations about astrophysics. Okay, so I try to focus on the instrument, which is the part that I better know, of course. Now let's switch to the spectroscope, and we'll talk about the architecture of the instrument. We'll go in detail to the grating and the prism. Oh, there is still a French word in my presentation. And prism. Sorry for the French words. Maybe there are some. And we'll talk about the importance of the slit or the fiber in the case of the A-shell for you. And we'll talk about the guiding module. And I will spend some time to go in detail, in more detail, to the E-shell spectroscope. Okay. So this is probably the important thing. This is the general principle of a spectroscope. This general principle is really common to probably 98% of the spectroscope. So there are few cases where an instrument can work quite differently, but most of the instruments that we use in industry, in cosmetics, in agriculture, or things like that, so all the instruments in chemics, they are all based on the same architecture. And the idea, generally speaking, is that we have a point-like source at the input. Usually this is a slit in our case, and I will come back on that later. But the idea is that we have a point-like source, and we use the light coming from this point-light source to send it to a collimator lens. This lens is collimated in order to produce a parallel beam. Sorry, and this parallel beam is sent to the dispersion element, which is either a prism or a grating, or a combination of both. And then this element has the ability to give a different angle to the rays if they have different wavelengths or color. So all the rays, because all the rays here, well, I guess that you are seeing my mouse. Tell me if this is not the case. But all the rays that are enter into the dispersion element are parallel. And then all the rays at the same wavelengths, for instance, these red rays here, all of them are parallel in order to have a parallel beam. But all the rays of another wavelengths they are also all parallel. I'm talking of the blue rays here, but they are going into another direction. Okay, and this is the job of this dispersing element to do this separation of the angle of the separation angle based on the wavelengths. Okay, and after that, we just have to put, I would say, to put back another lens, which is very comparable to the first one. And in this case, this lens will do exactly the symmetrical operation than at the beginning. So all the parallel beams will be focused or concentrated on the sensor, usually a CCD or CMOS camera. And they will be focused in the plane of the detector, the sensor. But of course, because they have different angles, the position on the sensor where the light is focused is different depending on the wavelengths. And this is at the input, we have just a point, and at the output, we have the same light source, but it is spread out along the sensor. Okay, so I will reuse this graph many times during my presentation, but this is really the key. And what I can say here also is that you see that we have one collimator which has its own focal length, and it must be collimated. It must be focused on the light source, on the slit, and to make a parallel beam here. And you also have an objective lens with another focal length. And you can play with these two focal lengths. So by selecting properly your optics, your lenses, you can use that to make a focal reducer. It could be also a focal multiplier, but most of the time this is a focal reducer. So by doing that, you can have inside your instruments, you can have a focal reducer. And the advantage of a focal reducer is that it will concentrate the light with more. If you have small pixels here, it will allow to focus, to better focus and concentrate the light on the pixels. I hope you are still here. This is fine because on my side, for the moment, I have absolutely no feedback. So I hope that you're here. And I cannot see your face, and I cannot see if what I'm saying is understandable. So tell me, don't hesitate to react. Okay, I'm checking. Yes, yes, I think you can see me. Here, you can see me. I will now focus on the dispersing element, which is the oh. I cannot see you anymore. Are you around?
Sorry,
Merci de vous déconnecter au moins pendant le cours, s'il vous plaît. Merci. Au moins, vous déconnectez.
Sorry, François, we have a problem with the internet issues, so you can resume again.
Okay, so what okay, I will screen again.
So yeah, you can share your screen.
Yes. So when did it stop?
Slide 7. Well, let's say your screen. Can you share it?
Yes.
It's coming.
Okay.
Yes, go ahead. Go ahead, please.
Okay, so did you have the explanation of the different elements in these schematics? Hello?
You can just start from 7.
Okay, so what I was saying is that well, I don't know if you had the beginning of this slide, but we have a light source here, and we need a light source at the input of the instrument, which is a light source is a point-like source, and either we consider a star is a source, a point-like source, or we use a slit, which is the case most of the time. And the light that comes out from this source is sent to the collimator lens, and this collimator lens will collimate the beam, the optical beam, and then so collimating means that it will be transformed in a parallel beam out of this lens. Okay, and then it is sent to a dispersing element. Dispersing element is either a prism or a grating. And this dispersing element is the key, in fact, in the spectroscope, because it will give a different direction to the rays that have different wavelengths, but it will give, of course, the same direction to all the rays with the same wavelengths, same color. Oops, sorry. Yeah. So it means that all the rays, all the red rays, for instance, here, so with a wavelength around, I don't know, 650 nanometers, will go out with a certain direction, and all the rays of the same wavelengths will go in the same direction. But the other rays of another wavelengths or color will go in another direction. Okay, and after that, we just have to add an objective lens, which is symmetrical to the collimator, and this will do the reverse job, which is to take the parallel beams and focus them on the sensor. Okay, and this the point is that because the direction are different depending on the color, on the wavelengths, then the position where the image is focused is different on the sensor. Okay, so this is really the key, because at the beginning we have one point, and at the end we'll have multiple points, and in fact multiple images of the light source that will be sent to different position on the sensor. So then the initial point is transformed in a line, vertical in this case, in a line depending on the wavelength. Okay, so now I will focus on the. Maybe I can do that on the dispersing element, which is the prism or the grating. Okay, to see more in detail how it works. Okay, so this dispersing element, it can be a prism, it can be a diffraction grating, or it can be also a combination of both. And I will show you an example with the LP600 in our product range with a prism. So regarding the prism is just a piece of glass with a polished surface. And so we can see here the section of the prism, which is a triangle. usually. And the idea is that we use the fact that that when the light crosses a surface, an optical surface, like it goes inside a piece of glass, then there is a phenomenon that we call the refraction that gives a different angle. So it will change the angle. You have an input angle here compared to the normal surface of the prism, and it will give a different angle to the output of the ray. But so this is what we call the refraction. But what is important for us here is that the refraction angle will depend on the wavelengths. Okay, and this is really the key of the principle of the prism. So we have a refraction here, we have a second refraction here at the output of the prism, and then first we have a different output angle that we call the deviation, but we also have different angles for the different wavelengths. Okay, so this is really due to the material itself. And this angle will depend mainly on the glass that we use. So we have, depending on the material itself, you have some glasses with a low dispersion and glasses with a higher dispersion, which is really dependent on the glass itself. So it means that if you want to select the dispersion angle, you will have to choose in a list of available glasses. Okay, there is also the geometry of the triangle that has a small effect, but the effect on the dispersion itself is very low. The effect will be more important on the deviation. What you have to keep in mind here with the prism is that the dispersion is very non-linear. So in some cases, this is really a problem because it means that the dispersion in the red parts of the spectrum will be much slower than the dispersion of the blue part. And when you are designing an instrument, this is really a hard constraint. We'll see that on the E-shell, where in the E-shell we have a prism that is used to do what we call the cross dispersion, and then it gives that the distance between the orders is much smaller for the red orders than for the blue orders. Oops, sorry. I'm afraid that it will happen several times. The other point is, which is very important, one of the advantages of the prism is that the Wool energy that goes inside into the prism goes out in a single spectrum. So its efficiency is very high, especially because we'll see that this is different with the gratings. And the last point, maybe, which is to mention here regarding the prism, is that this is a device which has a quite low dispersion. So if you want to have a low resolution spectroscope, you can really use it. But if you need to have a high dispersion, in almost all the cases, we are using grating, which is able to have a higher dispersion. Okay, now let's talk about the diffraction grating. In this case, so this is again, this is another way to spread out the light and to be the core of the spectroscope. In this case, the diffraction, the dispersion does not depend on the material, but it depends on the geometry of the grating. And the geometry is also usually, this is a piece of glass, or it can be a piece of aluminum, but most of the time this is a glass. And we engrave a high number of lines per millimeter. Sorry. In this case, we have just drawn a section of the grating. You have to imagine that the graves are across the figure here, and they are going this direction, this direction, this direction. Okay, of course, this is a 3D device, and but I've just shown here the section. I recall this is not you. Sorry. And what I want to show you, which is important here, is that because the distance of each groove here, each line, engraved line, because they are very small, and they are very small compared to, they are so small that the distance are comparable to the wavelengths of the light, then for this reason, each line will behave as a diffraction source. So when the light comes in such a groove, it will be diffracted. So it means that it will be sent to any direction as an input. So if you send some light in this direction, you will have some light going out in all the direction. Now, if you take these two specific rays that goes to these two specific summits, you will see that there will be a small delay. So this ray will need some more time to go up to this this summit compared to this one. Okay, and this delay will have some length, given by the distance between the lines and the angle of the light source. Okay, compared to the vertical in this graph. And this is also the same. So imagine that you have light that is sent to any direction at the output. But if I take a special direction, this one in my graph, I will have another delay between the two lines here. And if I add this delay plus this delay, in this specific direction, I will have exactly one wavelength length, in fact, and the delay will be the length of the path difference will have exactly the same length as the wavelength of the light. And then in this case, all the rays that goes to this grating, you can imagine that there is one way on each summit here. All these lines, all these rays will be added because they will be in phase. Okay, there will be only a split by one wavelength of the light. And in other direction, you have also some light that goes in all direction, but in the other direction, the distance, the path difference will not be a multiple of the wavelengths, and then all the rays and all the waves of the rays will be mixed, and then at the end they will be cancelled. So it means that in one given direction, and only one given direction for one wavelength, you will have exactly the addition of all the rays. So as a result, as a result, if you illuminate your grating in a given direction, there is one direction at the output where the light will go for a given wavelength. Okay, and then you can imagine that you will have a different angle here that will correspond to another wavelength. So at the end, we will have the same effect as the prism and the effect that I showed in my previous slide, which is that at the end, all the output angles will depend on the angle. The angle of the output rays will depend on the wavelength of the light. Okay, and there is something which is also important to understand here, is that if you have one wavelength, this distance d, which is at the end the path difference between these two rays, if you have one wavelength, then all the rays will be added. But you can find another direction where you will have two wavelengths. And in this case, the rays will also be added, but in another direction. And this other direction is what we call the second order. So the first order correspond to one wavelength, the second order to two wavelengths, third order to three wavelengths, and so on. And it can go to very high orders. And by the way, you can also have a -1 order in the other direction, which is symmetrical to this one. Okay. Well, I checked the image. I see that you are still there, so I guess that you can hear me. Then I continue. There are two kinds of gratings. The first one is the reflection gratings. So this is what I showed in the previous slide. You have some material here. Usually we have a very reflecting coating on the grating, like aluminum or even gold or silver or things like that, to have a very good reflecting rate. And in this case, when the white light arrives in this direction, it is reflected with an angle that depends on the wavelength. Okay, but this is a reflection system. We can also have a transmission grating. In this case, we don't put any opaque coating on the glass. We let the glass, the light going through the glass, and but the geometry is the same. And as a result, from an optical standpoint, this is exactly the same behavior. And then you can really do the same calculation. The only difference is that the light in this case goes through the grating. Another element here, you have probably heard about the blaze angle of a grating. And the idea is just that, I just explained that you have different orders in a grating, and that makes that all the energy of an incoming light is not sent back to a single order. It is sent to different orders. And of course, this is a problem because it means that not all the energy of the light coming from the star, in our case, will be used, and we will lose a part of the light, which is a pity, of course. To avoid, or oops, sorry, to reduce this phenomenon, there is a very clever system, very simple system, which is that we give a special angle to the grooves. So they are not symmetrical as they were in the previous slide, but we give a special angle, which is what we call the glass angle, in which, in fact, for given wavelengths, the optical faces here, or surfaces, will work as a mirror. So if they are working as a mirror, they will be much more efficient. And this very basic system will make that we'll be able to give to send much more energy in a given order than in the other orders. Okay, and this is important. So I like the graph below, which is an old graph. It was so these are not stars, but it was a test on a bench. It was interesting with a star analyzer. And in fact, we have here some light source, and you can see here that, so this is the 0th order. Well, by the way, I didn't talk about the 0th order, but this order 0 means that the grating works as a mirror. And then if you go, I can go back to this slide. If you go exactly in the same direction as the input light, then everything is symmetrical, and then there is no delay of the different rays, and then again all the rays can add all together, and you will see something, and this is what we call the 0th order. And in this case, there is no dispersion because all the wavelengths will have exactly the same direction because it works as a mirror. And in this case, on this graph, this is the 0th order, so there is no dispersion, and you can see the first order on the right, which is very bright. You can see also the beginning of the 2nd order, which is much fainter, and you can see here the -1 order. And what is important is that we can see that we concentrate much more light in this order than the other ones, okay? Anyway, what you have to think about is that with a grating, you will have different orders, then you will never have the same efficiency as with a prism, okay? So like always in optics, there are trade-offs, and you never know exactly. So there is no perfection. In fact, you have choices. So both the prism and the grating has advantage and drawbacks. Okay. Now I come back on this general graph, and I will try to give you some examples of real application of this schematic. The first one is the LP600, which is one of our entry-level spectroscope in our Cheliac product range. Maybe you are familiar with this instrument. The LP600 is this small device. It is only a few centimeters long. Okay, this is a C8 telescope. This is my old telescope, and here you have the acquisition camera. You have the LP600. You have the guiding module with the guiding camera in blue, and you have the calibration module, and then you have the attachment to the telescope with a focal reducer here. Okay, what I want to focus on now is this small LP600 device. You can see here is the architecture of the LP600. This is exactly what I explained in the previous schematic. You have the telescope beam that goes into the slit. We have a small slit in the LP600. And then you have behind a collimator lens. In this case, this is a doublet, an achromat doublet. And you have a grism. And the idea of the grism is that this is a combination of a prism and grating. So you have, this is a prism because you have an angle of this face here, but we have engraved a grating on this surface, okay? And at the end, you have the objective lens, which is another achromat doublet, and you have the CCD sensor. Again, you must have, I don't remember exactly, but you have only maybe 5 or 7 centimeters from the slit to the sensor. This is a very small instrument. In this case, you may ask the question, why did we choose to use a grism instead of a prism or a grating? In fact, in this case, the advantage is quite simple. If you are using a grating, you will have, of course, a quite high dispersion, and we use this high dispersion in the LP600, but you will also have a deviation angle. You always have a deviation angle. And in this system, we are using the prism to compensate for the deviation, to make that the output beam is on the same axis as the input beam. And this is what makes possible to have an instrument which is around a symmetrical axis. And then this is a very compact instrument and simple instrument to machine, and there are simple parts to machine. Okay, so this is why it makes possible to have a so compact instrument. Of course, the prism will also put some dispersion on the prism, but it is much lower than the grating. So at the end, we can consider that the grating makes the dispersion and it gives some deviation, and the prism is here only to compensate for the deviation. Are you still around?
Still here, François.
Yeah, okay, perfect, thank you. Okay, now I do have another example, which is the LRS3, which is, of course, another instrument in our product range. The LRS3 is, it was the first instrument that we made in the history of the company, and even before we create the company. And this is a high resolution instrument. The LP600 is a very small instrument, a few centimeter length. This one is a little bit bigger. So I think roughly the length of the base here is something like 250 centimeter and 50 millimeter, okay, 25 centimeters. And the height should be something like 20 centimeter. Okay. So you have the telescope in an entrance here, input. You have the guiding port for the guiding camera, and you have the place here to put the camera for which you will acquire the spectra. And we have here a small micrometer that allows to change the grating angle. Again, if I look at inside this instrument, I will find exactly the same optical architecture, even if the mechanical architecture is quite different. Sorry. In this case, again, we have the telescope beam that comes here, which is at f10, so it is much faster, much slower, sorry, than for the LP, and it goes through the slit, which is at this position, and after the slit, it is sent to a small mirror at this position that gives a right angle to the beam. And here we can find the collimator lens. And so the black lines here are the parallel beam that we send to the grating. And in this case, this is a reflection grating. In the LP, it was a transmission grating, of course. In this case, this is a reflection grating. And this is the specificity of this instrument, which this is what we call the litho architecture. In fact, this grating sent back in almost the same direction the light, and then we reuse a second time this doublet, this time as the objective lens. So in fact, we have only one doublet in the instrument that makes the collimator and the objective lens. And after that, this doublet will concentrate the light on the sensor on the CCD or CMOS detector. Of course, there is a small angle, so it is not in the plane of the image here. There is a small angle given to this beam to make sure that the return beam here, the colored beam, is not sent back to this small mirror, but it goes just beside the mirror. Okay. Now I want to talk a little bit about this slit, which is another key element of the spectroscope. Maybe just a small pause if there are questions, or is it clear? No, no question.
I have a question, please, François.
Yep.
Yeah. The dilemma is between flow and resolution. What is the compromise and to make equilibrium the best flow to have a good diameter of telescope and the maximum of resolution? You know, for example, if I have a spectrograph which have 50,000 resolution and I have an aperture in an inch, I think that there is no equilibrium. What do you think?
Well, so well, I'm not sure to have properly understand your question, but what you are saying is that
it's the good telescope for the good spectrograph.
Yes, so this is what I will talk about in coming slides. But of course, what you are saying is very important, because for the moment, I'm just talking about principles. I'm not talking about dimensions. But of course, when you want to put some real dimensions on this, this becomes more complex, because for a given telescope with a given aperture, and by the way, the aperture of the spectroscope here, the angle of the input beam here, of course, must match the telescope aperture itself. I will have few graphs about that later on. And so you have to match your optic to the telescope. And of course, you will also have to match the dispersion element to have the right resolution, so the resolution that you are looking for. And all this requires to do some dimensioning and to select the right components, prism or grating, and the right element and right optical diameter. You have to define, for instance, the beam diameter that will be one of the main dimension of your instrument. You know, and there is one other thing, which is you have to adapt the slit size, which is here, to the pixel size, which are here. Okay, and again, I have a slide about that later on. But I'm not sure. Did I answer your question, or did I miss it?
Relatively. Une partie. Je pense après, avec les slides qui vont venir.
OK.
OK, ça va compléter. Merci.
OK. So let's focus on the slit itself. I told you that we have to have a point-like source at the input of the spectroscope, and one of the way to do it is to put a slit, a very thin slit, at the input. But we are also we can consider that in fact we are observing stars, and stars are like points in the sky. So we can, and it happens that we are using a slitless spectroscope. And the case of this star analyzer in our product range is exactly that. We just put a diffraction grating in the light path in front of the sensor. So in some cases, it can be either it can be in front of some optics, or it can be between the telescope and the in this case the DSLR or the camera. And the huge advantage of that is it is very simple. So it means, of course, it is inexpensive, because this is like a filter that you have to put in the light path of your instrument. So it is quite inexpensive. And also this is very efficient, because the light is not going through a high number of surfaces. So the overall efficiency of the system is very good. And what you will see is something like that. So you will see the zeroth order of each star. So you will see exactly the same field of view and the same stars that you would see if you don't have the star analyzer. Again, sorry. If you don't have if you wouldn't have the star analyzer, but each star has its own spectrum. Okay, this one, for instance, has this spectrum. This bright star has this bright spectrum. This star here has this spectrum, and so on. You know, this one has this spectrum. And in this case, it was close to the M57 object, the planetary nebulae. And you can see in this case that you have the zeroth order of the planetary nebulae, And in this case, this is not a continuum because a planetary nebula has few emission lines. And then as a result, you can see few images, secondary images at different wavelengths, which is very surprising in this case. And so this is a very good example. In this case, it works very well. And this is an interesting image. But the problem is that by doing that, you have, so the advantage is it is a very high efficiency system. The drawback is that you have a lot of spectra that are mixed with a lot of stars. For instance, here you have a zeroth order of a star and you have a spectrum. And you can see that the spectrum is mixed with another star. And if you analyze this spectrum, and if you don't take care about this star, you will see a huge emission in your spectrum, and you may think that this is a real phenomenon, which is not the case, of course. Okay, so this is one of the problem with the slit, with the slitless, with the absence of slit. Now, if we have a slit, and here is, for instance, the slit of the Alpi or the UVEX. So this small aluminum part is something like 25 millimeters, about 1 inch diameter. And this is a small part of glass with some reflecting surface. And you can see here the slit, which is just 3 millimeters long. Okay, so all the rest of the surface is a mirror, but there is just a slit engraved, a slit of 35 microns in this case, engraved in the glass. Okay, so it's very small. And this is just to show you exactly what means a slit. So in this case, the surface is roughly 13 by 12 millimeters. And there is something that maybe we don't see very well on this picture, but we give an angle to the slit, and I will explain you why later when we talk about the guiding module. Okay, so in fact, the thickness here is small, is maybe 1 millimeter, and it is probably 3 or 4 millimeters on the other side, okay, to give an angle to the slit. And by using a slit, we have many advantages. And the first is that there is no more overlap between the stars and the spectra. I told you that in the previous image, you saw that we had several spectra. In this case, imagine that this is the field of view of your telescope. So we are at the focal plane of the telescope in this image. This is what you will see with the guiding image if you have a guiding device. And in this case, if you make sure to have one star in this slit, you will have one spectrum, even if there are other stars in the field of view. Okay, so this is the first advantage. The other one is that you can put some extended light, extended object in your slit. You have seen with the M57 planetary nebula in the image before. In this case, this is great because you have few emission lines, so you have few images of the nebulae. But if you had a normal spectrum for a star, a continuous spectrum, all the images of the object will be mixed, and at the end you cannot recognize anything. If you put this slit here, you can isolate a very small width of light, and this is this portion of light that is spread out in the image. And again, here you can see that all the slit has a spectrum, gives a spectrum. And again, I say again that a spectrum is a multiple image of the slit. So this is very important to understand. So in this case, I've put these small lines to show that we see the edges of the slit, because we see that the emission lines are have the same length, the same height as the slit. In this case, these are different emission lines due to the light pollution, because this image was taken in a very polluted sky. and we have put the threshold in order to see the background. And of course, the star spectrum is totally saturated in this case. But you can really see that the spectrum is a multiple image of the slit and all the light that is going into the slit. So you can put some extended objects. In this case, if you put your M57 object or any nebulae or galaxy or something that has a surface in the sky, you can isolate a part of this object and make the spectrum of this object, and then you can even, if you want to have the whole spectrum of the whole object, you can even scan the object and take many spectra by moving very slowly the slit across the object. Another advantage of using that, well, something which is very important is that when we use a calibration lamp, then this calibration lamp is like an extended object. So the light source is not point-like. And then if you don't use a slit, you cannot use a calibration lamp. And especially for the when I come back to this star analyzer image, in this case, with the star analyzer, you cannot use a light source because calibration light, sorry, because you will have a multiple image of your slit and everything is mixed, and at the end you will have some white light in all your image. Something also very important when you are doing spectroscopy, you can see here that we measure the sky pollution across the slit. And somewhere, this is a good news because this star spectrum is affected by the light pollution. But when we record the spectrum with a slit, we also record the spectrum of the sky pollution, which is, again, the sky background is an extended object. So for the same reason, we can record the sky background, sky pollution at the same time. And then during the data processing, we'll be able to compensate, to correct the star spectrum from the sky pollution. And of course, you cannot do that with the star analyzer. And another point also is that if you have tracking issue, if there is some wind during the observation, or if the motor is not very stabilized and you have some movement and periodic corrections or things like that, maybe your star will not stay exactly at the same place. So if you don't have a slit, this movement, the tracking issue during your observation will have a direct effect on the resolution of your spectrum. Okay, because for the same reason, the spectrum is a multiple image of the source. So imagine that you don't have the slit here and the only source is your star. If the star is moving, then you will have multiple spectra that are mixed together. And at the end, the result is that you will lose resolution. With a slit, if you have the same problem, then you will lose some light because you will not have all the possible light, all the possible photons into the slit, but all the photons that goes into the slit will have exactly the same position. And then you will have, a correct spectrum. So this slit allows to give a constant resolution, whatever happens with the telescope in front of the spectroscope. And by the way, the guiding system also the slit itself allow to make some a device to take care of the guiding, because at the same time as you are recording your spectrum, you also you are able to see the field of view of your telescope.
So I have a question.
On a une question?
Yes.
Okay, so thanks. I was just wondering if the same level of correction will happen if we have a thunderstorm. So, for instance, if the sky is polluted, yes, the whole adjustment that happens with the slit can make a correction. That's my understanding. But in a thunderstorm, you pretty much have a charged atmosphere. So a charged atmosphere is not just about dust and particles. It's also about the behavior of it's chemical, in other words, the behavior of charges. It's electricity, static electricity, if you like. So yeah, is it possible to also have a correction and have work done in that kind of environment?
Oh, well, this is a very interesting question. I cannot tell you. I would say something very basic. What we're observing is the light. If your static electricity makes some light, we can see it. If it doesn't make any light, we cannot see it. I don't know if I don't know how it is possible. So what is the? Of course, if you have a strike in the sky, you may see it, but I guess if you have a strike, you are not observing. In fact, I guess, and well, I don't know. Again, what we're observing is the light. Does the effect you are talking about make some light or not?
Well, it could make some light. It may not make some light. But the situation, whether it makes light or not, in terms of the charged atmosphere, in terms of static electricity, it might be the problem. And it could also be the light. I don't know how that would play out in such an environment.
What I know is, I like to always come to very basic things because I'm a simple guy. Is that all what you will see on your sensor, because the sensor is sensitive to the light, is the light that goes into the slit. So if you have some light that goes into the slit, you'll see it. Well, I mean, in the wavelengths where the sensor is sensitive, of course, then you will see something on your sensor.
Thank you very much.
I have another question. Can you please can you hear me now?
Yes, I can hear you. Yeah.
Okay, you were saying that it's not very well affected when we are using the slit. It's not very well affected by the guiding errors and stuff. Therefore, it's less affected also by seeing, if the seeing is very bad. So what are the limits? I'm trying to conclude, but I might be mistaken. So what are the limits? Thank you.
You are totally right. Yes, what we are saying is important. In fact, let's be very clear. With the slit, the resolution of your instrument only depends on the slit. Okay, so you will not lose resolution if you have problem with trackings or what kind of problem at the input. But of course, you may lose some light. So you may lose some signal to noise ratio if you are losing light at the input. Okay, so you are keeping the resolution, but it is always very important to keep as much as possible all the light into the slit. But now what you are saying is also very important, is that thanks to the slit, your observation, that the resolution of your observations will be constant, whatever is the seeing. If you observe one day the seeing is perfect and the day after the seeing is worse, if you don't have a slit, you may have different resolution, and really the resolution may depend on the general observation conditions. If you have a slit, again, if the seeing is poor, then the size, the star image at the focal plane will be wider, will be bigger, then you will lose some light, but you will not lose some resolution. Okay? Okay, I continue. Now, so, well, this is interesting because I'm talking about resolution, and let's spend some time on what exactly means the resolution. So the resolution is the ability to see some details in the spectrum. So here are, well, there are very old spectra. I like to reuse these images, but this is two spectra of the same star, of Vega in this case. In this case, this is a low resolution spectrum. Again, this is a very, very old observation. We should do much better today. Anyway, the idea is here. This is a low resolution, and this is a high resolution of this special part, which is the H-alpha line, which is usually the most important line to observe in a spectrum, the first one probably to observe. And in this case, we see that even if we have the same sensor size, so if the total length of the graph is the same, we can see much more details in the high resolution than in the low resolution. Okay, so this is really, we can compare that with a photo lens. You can have a wide angle photo lens, or you can have a tele lens, and the both will have very different results. In one case, you'll see the whole landscape. In the other case, you will see only a small detail of your landscape. I just want to draw your attention on the fact that when we are talking about resolution, we very often confuse with the dispersion. The dispersion is the extension, the physical extension of the spectrum in nanometer per millimeter. So in other words, if you have some blue light at 400 nanometers and some red light at 700 nanometers, the dispersion is how many millimeters separate these two spots here. And this is the dispersion. Okay, so this is really the physical effect of the spectrum. Now, the resolution depends, of course, on the dispersion, but it's not enough. It also depends on the light source size. And here we start understanding that the slit width becomes critical, because in this case, in these three lines, the dispersion is the same because the distance between the blue and the red spots are the same. But here you can see that we can perfectly distinguish the different spots, where here all the spots are mixed. Okay, and then the resolution will be much better in this first line than in the bottom line here, where the dispersion is the same. Okay. Now, this is a question. I know that in our history, in the adventure of Shellac Instrument and all the people who work on this project before we create the company, we started with the high resolution, and we did consider that in fact the high resolution is the best. So high resolution means high quality, and that's natural. And we saw that, well, the low resolution is maybe not so important. In fact, this is absolutely not true. Both high resolution and low resolution have advantages. The high resolution will give you a lot of details in your profile. For instance, you can see a lot of atmospheric lines here in the profile of Vega, which is very useful to calibrate, by the way, the instrument, where in this case, you don't have enough resolution to see all these small details. Okay, and if you want to have small details, and especially I'm talking about the Doppler effect of radial velocities, sorry, yeah, of the radial velocity. So I'm sure that you have already heard about the Doppler effect that moves the spectrum depending on the speed of the light source on the axis, the due axis. So if the object comes towards us or moves away from us, then it will move the spectrum. And in fact, the idea is that the general figure is that when you have a movement of 50 kilometers per second, which is on Earth quite high, but in space this is very common, it gives a Doppler shift of about 1 angstrom. Okay, and of course, if you want to see such details, you must have some high resolution. Again, this is generally speaking. We also have some methods to integrate a lot of lines and a whole spectrum and so on. But generally speaking, if you want to do some radial velocity measurements, you need to have a high resolution system. On the other side, the low resolution have an extended wavelength domain. And if you're observing an object and you want to know if there is helium and if there is carbon, and if there is I don't know if the H alpha and H beta and H gamma lines are in emission or in absorption, then you need to have this whole landscape that is given by the low resolution system. Also, something very important in practice is that the exposure times for same star will be much lower in low resolution than in high resolution. For a very simple reason which is that in high resolution, on a given pixel, you have a very small bandwidth that is concentrated, that is sent to this pixel. In low resolution, you will have much larger bandwidth that is sent to the same pixels. And then you will have more light on a pixel in low resolution than in high resolution. So this is important because I know that generally speaking, if I compare with the LP600 and the LARES-3, which are both some amateur instruments, I know that during one night with the LP, you can observe, I don't know, 20 objects, 25, 30 objects. In the high resolution, you will have only 4 or 5 objects, because in low resolution, you'll need a few minutes to observe one target. In high resolution, you'll need roughly 1 hour or 2 hours. Okay, so this is a very important constraint when you want to observe, to organize your observations. And by the way, also for the same reason, which is that you send more light, a bigger light bandwidth on a given pixel in low resolution, you'll be able to observe much fainter targets. Okay, this is absolutely necessary. If you want to observe very faint galaxies, then this is almost necessary to work at low resolution. And then if you need absolutely a high resolution on faint targets, then you'll have to have a big telescopes. Okay, and this is almost not negotiable. Okay. Now, when I look at I come back to this schematic and say, okay, where this resolution comes from? It comes from few parameters. And then I think that Abdelmajid will start entering in the questions that you asked. The first point, of course, is the grating density or the material of your prism that will, you have understood that the more grooves per millimeter you are engraving, will have in your grating. So the first parameter, of course, is to select the right grating density, so the number of lines per millimeter. But this is not enough. This is not the only point. The other point, which is very important, is that you must select the right slit width, because remember that a spectrum, in fact, is a multiple image of the slit on the sensor. And then, of course, if you have a wide slit, you will have a wide image on the sensor, and all the different images will be mixed, and then you will not be able to see small details. Okay, and sorry, the other point is, and in fact, this is not really the slit size which is important, but this is the slit size seen from the collimateur focal length, which in fact, this is the angle of the slit from the focal length. This is the, if I would draw some lines here, this is the small angle of the slit seen from the collimator lens. And really, if you want to increase the resolution, either you change, you select more dense grating, or you increase the focal length, or you close the slit. But we'll see that, of course, the slit has other impact that you cannot afford to do anything with no constraint. Okay. See that the room is still there. So
yeah. So we have perfect to 5 o'clock, so we can make a break or for first person.
Okay, so we can stop here if you want.
Yeah, 10 minutes.
Okay, 10 minutes, no problem.
Okay. Donc, on prend 10 minutes, 10 minutes de break. You have a question? No. Okay. So, oui.
We still have time.
Yeah.
We still have time.
Yeah, what did he propose? Parce qu'il y a deux parties. À 4 heures, qui se passe chez voilà. 4 heures. Bon, c'est pas grave, après nous créons la pause café.
C'est le plus marrant.
Bon, c'est pas grave.
C'est une partie pratique après? Non? C'est encore.
Ouais, mais c'est plus la seconde. Tu veux continuer une demi-heure ou on arrête 10 minutes? Parce que là, la pause café, normalement, c'est prévu à 4h30.
Alors, moi, c'est absolument comme, moi, c'est comme vous voulez. Hein. Je peux continuer ou m'arrêter. Je m'adapte à vous.
Ok, alors on se donne, pardon, excuse-moi. On se donne encore 30 minutes et après on fait la pause. Ça te va? Merci.
Ok, c'est parti. Alors, okay, so now the question is, there is something which is really complex. This is like always in optics, that we have very complex trade-off to do, because the slit will be as small as possible to increase the resolution, as we have seen. But the problem is that the slit must be also wide enough to get or to collect all the photons from the telescope. And you know that, in fact, the star image size at the focal plane of the telescope depends on the focal length of the telescope and on the seeing. Okay, and then for sure, if you want to work with a big telescope for a given resolution, it means that you will have to increase the slit size proportionally to the size of the telescope. And if you do that, and if you want to keep the resolution, the same resolution, it means that you'll have to increase also the size of the spectroscope. Okay, so really there is an optimal position to find on the slit to make sure that we can collect all the light and we can have the resolution that we need at the end. And this is always a complex trade-off. And again, this is why if you need this resolution for this kind of object, and then you need to have a bigger telescope, and if you need to have a bigger telescope, you need to have a bigger spectroscope. So there is no magic, and this well, again, there is no negotiation. And by the way, this is something which is important to understand. For this reason, it is easier to do spectroscopy with small telescopes. And this is something which is very important, because when you are talking on a small telescope, I mean, well, I don't have any limits, but it can be a 20 centimeter, 30 centimeter, or for in some cases, we consider that 50 centimeter is still a small telescope. Then the slit size, which is linked to the star image size at the focal plane, is quite comparable to the pixel size we have today in most of our cameras. Okay, if you want to have a bigger telescope, you will have to have a bigger slit, but in this case, you will have to compensate this bigger slit by a focal reducer inside the spectroscope to make sure that it matches the pixel size. Okay, so I hope I'm clear enough. This is something, the key, in fact, at the end is that it is easier to do spectroscopy with small telescopes, which is, for a lot of people, it is you need to have a big telescope to do spectroscopy. This is false. You can do, and it is easier to do spectroscopy with a small telescope. Now, let's talk a little bit about the guiding module. You know that well, when you have a slit, we have seen that there are many good reasons to put a slit into in front at the input of the spectroscope. The problem is that you don't see anymore the telescope field of view. Yeah. No, you cannot see the field of view of the telescope. And then this is a problem because you have to find the right target, the right star. And if you cannot see exactly which one it is very difficult to just base your observation on the coordinates of your telescope. It's not precise enough. And then you have to see the field of view, and you have to also see if the light of the star is properly injected into the slit. And then we use a guiding module to do that. And the idea is that you have the telescope here, which is represented by a simple lens. Even if it is more complex, we can always consider that the telescope is like a lens. And if you look at the black rays, they are on the axis, so these lines, these rays, come from a star on the axis of the telescope. And in this case, the telescope concentrates these rays on the slit, and these rays go through the slit and go into the spectroscope and makes a spectrum. But if you look at a small angle, so if you are looking at another part of the field of view of the telescope, another star or sky background and so on, then, oops, sorry, then in fact, these rays will not go into the slit, and they will be reflected by the slit, because remember that the slit, in fact, it is a mirror slit. So all the surface out of the slit is a mirror. Then this light is sent back thanks to the angle here with a small deviation. And then we have another guiding mirror here. And we have that sent the light in this direction. And then we just have guiding optics here to concentrate and to refocus the image of the field of view, to concentrate it on the CCD. Okay, so if we do that, in fact, we see this guiding image on this camera, and then during daylight, we can see something like that. So you can see the sky surface, and you can see the slit in the middle of the image. Okay, so this is the way where the best way to do this guiding. And by doing that, we can see exactly if we are in the right field of view and if we are talking about the right star. And also we can ensure that the star is sent to the guiding image. By the way, so this is a question that comes, I guess this is not the case for you, but when I'm talking to amateur astronomers, there is often questions about, can I have a parallel telescope as a piggyback on the telescope to do this guiding in parallel, like we do usually in imaging? And my experience is that no, well, technically, in theory, this is possible to do it. But the problem is that if you do that, you don't see exactly, you don't see where is the slit. So you cannot ensure that you are perfectly putting all the light of the star in the slit. You can do some precise guiding, but you don't see where you are guiding, in fact. So it's not very useful. Okay. And whoa, again, sorry. And well, this is something. Well, this is an image that I've taken on my system a few days ago. I was just doing some tests and.
We have a question, please.
Yeah.
Okay. Go ahead.
Sorry, Doc, I'm a bit concerned about the occupational hazard of using a spectroscope. So you've talked about, you know, having all the almost 100% of the photons into the slate, and with all the spectrum coming in. And I mean, some question can go to anybody who is using a telescope. What level of damage does this do to the eyes? Does the spectroscopes have the inbuilt protections for the observer? Or how does this work? Or is it a component that you have to get separately to work with the spectroscope? Over.
I'm sorry. So the sound quality is not good, and I didn't understand your question. So can you repeat?
Someone using a spectroscope protect his eyes from all the photons? That's like an occupational hazard. Does a spectroscope has a protection for the eyes?
For the eyes?
Yes.
You are talking about the
For the eyes. This is not manual view.
No, no.
Oh, okay. I got it mixed up.
No.
Fantastic.
So,
Okay. So, well, if I properly understand, you think you say, well, is it do I have to protect my eyes when I look at the system? But in all what I'm doing right now, I'm only talking about imaging, and you have a CCD camera at the end of the spectroscope, so you never put your eyes in the system. So there is no need to protect your eyes. Okay, it does not make sense because you don't put the eye in your instruments. However, if I take a small device, well, I do have one. Maybe I do have. Let me take. Yes, I do have one. This is my demo spectroscope. I'm sorry, I cannot. I'd love to give it to you to show, but this is a very small spectroscope. You know, to look, and this one you can use it by a naked eye. And here, when I look at it, I can see the spectrum of the sky background. And in this case, you can ask this question: is it dangerous or not? So, do I have to protect my eyes or not? In fact, there are two things. First, there is a slit at the input, so there is a very small portion of the light coming from the sky that is going into my eye. And the second one is that the light is spread out. So it's not as concentrated as if you looked with a binocular, for instance, at the sky. So in practice, if I do observe the sun with this system, because the diameter is small, because there is a slit, and because the light is spread out, there is in fact no danger. Okay, it's not more dangerous than looking at the sun with naked eye. Okay, so it's always important to tell everybody that be careful with the sun. It can be dangerous for your eyes, but in this case, there is no danger if I look. In fact, there is no magnification. In fact. Okay. So I come back on this image. So this is an image that I've taken a few days ago, and with I have a Richet Chrétien 8 inches telescope. It was made with the UVX, but we don't care because this is a guiding image, and it is the ALPI or UVX guiding module. And I also have a high performance slit that has a very good reflection rate. And I used an OISA2022 mini camera, which is really the great camera today for the guiding, because it has quite it has a big sensor and it has big pixels, so it's very sensitive. and it was a 5 seconds exposure. So I'm in France, in close to Grenoble in French Alps, and here is what I see. And in fact, this is you can see the slit. Well, because it was really the beginning of the night, and I am not in a clear sky. I am in a region where you can have some sky pollution. But you can see the slit here, and you can see the star field of view. So it's, sorry, again. You can see the star field of view, and you can see the slit, and then it's easy to recognize the field of view and to say, okay, so this is the star that I want to observe, or this star maybe, and then you can move the telescope slightly to put this star in the middle of the slit, and then you can either track and guide, auto-guide on the star in the slit, or you can also track on a slit, on a star out of the slit if you prefer. Okay. Now I want to spend some time on the e-shell, and especially because you have an e-shell at OK Medan, and maybe well, did you observe the days before with this instrument, or not yet, or do you have any plan to do it? Or?
Now we transform our money in at once spectro and photometry. You can choose for the same target as the main measurement for photometry measurement, and so we have 1 week break before the next observation.
Wow. Okay. Okay. Well, I will talk about this instrument and how it works, and because it is a special. Oh, sorry. It is a special device, in fact, compared to what I did explain before. And especially the first point is that the resolution power of this instrument is R is 10K, which is something that we consider as high resolution. So it depends on, of course, for some professionals, it can be considered as low resolution, but usually speaking, it is some high resolution. And the wavelength domain is 400 to 700 nanometers. And I remember that I told you that if you are doing high resolution, you will see a lot of details in your spectra. And if you are doing low resolution, you will have a large bandwidth and wavelength domain. And in fact, and there is a trade-off between these two parameters. And the e-shell spectroscope is a kind of magic solution to have both at the same time. So we have the high resolution and we have a wide wavelength domain covered by the instrument. And this is done by a very specific approach of the system, of the optics. So you should be familiar with that. So the e-shell itself is this instrument, and the e-shell spectra that you can see is something like that. And then you can see many lines, and in fact, each line is an order of the spectrum. And when I'm talking about orders, this is the same order as I talked about before with the grating orders. Okay, so in fact, in an e-shell spectroscope, we use exactly the same principle as before, but we are just working at very high orders. And we have a system, a cross-dispersion system that splits the different orders. And then we don't, the spectrum is not a single line anymore, but this is a multiple line system. And then each line has high resolution. And because we have a high number of lines, we cover a wide bandwidth. Okay, so I guess that this is, it looks like it is a sun spectrum. And in this case, we can see the H alpha line here. We can see, I think, the sodium doublet. We can see the magnesium triplet here, and you can see a lot of lines all around. Here you have the telluric lines in the red or infrared part of the spectrum. The e-shell, oops, sorry. the e-shell instrument that you have at UK this is on one side, on one hand, this is an E-shell spectroscope, so based on E-shell grating. And on the other hand, this is a fiber-fed instrument. And really, this is the combination of these two parts, the E-shell on one side and the fiber-fed on the other side, that gives all this advantage. You have the high resolution and the large bandwidth, and you have a high stability. So in this case, the spectroscope is not installed at the back of the telescope anymore. It is installed in a fixed room and in stable conditions, and even in a temperature control room. And then you have a very stable instrument, and you just have to use what we call a guiding unit that is here to catch the light at the back of the telescope and send it to the fiber optics, and then you send the light through the fiber optics to the instrument. So the using a fiber is a real advantage because of this flexion problem. But again, if you are using a small telescope, and again, a small telescope is probably up to 50 centimeters. If you are using a small telescope, it is also a very good idea to keep the spectroscope on the telescope, because when you are using the fiber, you may lose some light through the fiber, and especially through the fiber ends. Okay, so again, this is a question of trade-off. For sure, if you have a big telescope and you want to have some big resolution, the problem is that you will have big telescopes means big spectroscope. And if you are talking about high resolution, this is even bigger spectroscope. So if it is a big spectroscope, you will have necessarily some mechanical flexions, and it will be very difficult to have something very precise in terms of resolution and keeping the spectrum at the same place. So for big telescope, for sure, it's better to have this solution, and this is the reason for which all the major telescopes in the world, the biggest telescope in the world, are using fibers for spectroscopy. But if you are doing either a small resolution or you are using a small telescope, then it can be the good trade-off to keep it on the telescope. Well, this is a Vega spectrum, not very interesting, but this is the idea. In this case, we have put a DSLR, so a photo camera, a color photo camera, and in this case, you can see that the top orders are red and the bottom orders are blue, and then each order has its own color, because of course the whole spectrum, when you link all these orders together, it will make a huge and high resolution rainbow. By the way, we can see sorry, my phone. Here you can see an absorption line. So this is the H alpha, which is at 656 nanometer, which is in the red part of the spectrum. You can see again the sodium doublet. I don't know if you can see it on your screen. It's very faint here. And there is also something interesting. We can see the H beta line in the blue part. So H beta is 481 nanometer, I think. And an interesting point is that you can see this blue absorption line, and you have another one here. And in fact, this other one is the same, but you have some overlap from one order to the other. Okay, and in fact, this is a double image of the spectrum. And then, if you want to have the whole observation, you will have to rebuild, to merge all these orders by adding that signal to that signal. Okay. Now how it works? In fact, we just see the same principle as before. So you have a light source. So in this case, this is fiber. This is not a slit. This is a fiber optics. Usually we use 50 microns fiber optics. because usually we use small telescopes and 50 microns fiber is properly matching the small telescope star image sizes. You have the collimator lens, you have the objective lens at the end, and you have not one grating, but you have, in fact, you have one grating and a prism in the case of the e-shell. And of course, you have the sensor here. So you don't have only one grating, but you have only a dispersion element, but you have two of them. And the idea, in fact, is that we are using with an e-shell grating with a very small, very low number of lines per millimeter. I think in this case it is, 79 lines per millimeter in the e-shell spectroscope that you have. And where for the Lares 3, for instance, it is 2,400 lines per millimeter. So the e-shell grating has much less lines per millimeter. But it is made, we use it at very high orders, and the orders are 30 to 50. So remember at the beginning, I talked about the zeroth order, the first order, maybe the second, or maybe the minus one. But it is, we never talk about the order so high. And in fact, we are working with the orders 30 to 50. And of course, at the end of this main grating that we use at high orders, all the orders are mixed together, and because they are in the same direction. And then at the end, if I put my eye here before the prism, I will see a line with the white light, in fact, because all the orders are mixed. And in fact, the prism is here to separate and to split all the different orders in the other direction. Okay, so in this case, the lines on the grating are in this direction. So the spectrum is spread out vertically in this image, and then you go through the prism, and the prism will split horizontally the different orders. And again, we send that to the photo lens or the objective lens in order to build the image on the sensor, the resulting image on the sensor. Okay, so it is very different because what you see in the image is different, but the general principle of the spectroscope again is the same.
I have a question, please.
Yeah.
François, yeah. During our utilization, when you use this type of spectrograph, I think one of the weak point is the connection between fiber and the bonnet, and the fiber and the spectrograph. And the second one is the bonnet, you know, the optic system.
Yeah, what we call it then, yeah.
When the scope move, and it depends of speed, and if we have a shock, the alignment system can move. So we can lose about 20 to 30 of signal. So I think how we can develop that, or yeah.
Yes, okay. So you are talking about the yes, we put the fiber. We attach it on one side, we attach it on the spectroscope. So this is not very critical because, well, usually we don't have a problem on the spectral side. When we have problems, this is on the telescope side because the telescope is moving. And so the spectroscope side is not that critical, but on the guiding unit side, or the bonnet, or or what we call the FIGU, which is the fiber injection and guiding unit. In the guiding unit, yes, there is a very precise alignment between the hole in the mirror. I will show you between the hole in the mirror and the fiber optic itself. And I agree that if you push very hard on the fiber, and especially when if the problem if the guiding unit drops on the ground, or if you have a very strong contact with the mount, which happens from time to time, then there is a risk of misalignment of light. And if you have misalignment, I agree, you may lose a very high portion of the light, and this is a pity. Well, my experience says that if you break this alignment, you don't see anything else. So you don't lose 20% of the light, you lose everything. So you cannot see any more spectrum, even if you are sure that you are plotting at the right star. And this is something which is, I confirm, which is quite critical. And you need some tooling to redo or to repair this alignment. So maybe if you need it, we can discuss, and I can explain you how we do the alignment. But this requires small tooling to do it. In fact, remember that we have a 50 micron fibers to be aligned with the 50 micron hole, and you need to do that at something like few microns precision to have the best alignment. Did I answer your question, or I'm not sure?
Yeah.
Yeah.
What is the solution?
Oh, the solution is to not break the guiding unit.
Yeah, to change the guiding unit.
And
have you new one?
No, I think there is something which is that you can do. Well, I don't have this experience, but I know that somebody are doing that. Is from time to time, maybe every one time a month, you observe a known target that you perfectly know the level of signal that you can collect. Take a spectrum of 10 seconds or 1 minute acquisition, and then compare the light level you have in your spectrum without any processing, just in the raw image. Just have a quick measure of the level of light you have in your image to make sure that you still have the initial efficiency.
Okay.
And globally, I can tell you that it happens that some users send back the guiding unit to us for tuning. But, well, generally speaking, this is very rare, so it happens. But we have a lot of guiding units installed in the world, and only few units have been sent back. Okay.
Okay. So we have 5 minutes to half.
Sorry.
We have
5 minutes. Okay, so 5 minutes. Okay, just 5 minutes, and we have the break. Okay. Okay. This is just to show you. So this is the same the same schematic. So you can see here the fiber, the collimator, the grating, the prism, the photo lens, and the sensor. And when we put that in the box, here is the fiber input. We have at the base here, we have the collimator lens. We have the grating, the main grating. We have here the prisms for the cross dispersion, and we do have the photo lens and the CCD sensor at the top. Okay, so when you will see the instrument now, you can recognize all the elements. Regarding the fiber optics, so this is just a few pictures very quickly to show you what is the guiding optics. So the idea of guiding optics, not guiding optics, sorry, fiber optics. The idea is that we have two different glasses. This is a very small tube. So in our case, the blue part is 50 microns. Okay, so this is written 62.5 microns, but in our case, this is 50 microns. And we have the core, what we call the core, in which the light will circulate. And around we have a gain, I don't, or shield, I don't know the name in English, and with a different glass material. So you have an optical surface between the two, and then we can have many reflections inside the system. And because we select properly the different glasses, you have 100% of reflection inside the fiber. So it means that all the light that goes into the fiber goes out at the other end of the fiber, and there is almost nothing that goes out of the gain. Okay, so this is I think that this one is a 200 microns for the calibration. I see that because of the color, like I can see it looks like the thorium argon light. And but you can very easily check that the fiber is working, because you just have to look at the fiber at one end and put the other one in the direction of some light source, and then you perfectly see the small point here. And here you have also, you can see the core itself, you can see the shield around, and all this is the connector material. So to show you the side of the system, and you have different connectors for. Also, you have to know that you have different kind of fibers. You have some monomode fibers and some multimode fibers. Monomode means that it is made to really concentrate on one wavelength. But in our case, because we want to cover a very wide range of wavelengths, then we need to, we need to use multimode fibers. And maybe let me check. Well, okay. Well, maybe we can stop here. We can stop here, and I will continue with the gaining unit just after. Do you agree?
One question, please. I actually have one quick question. No, there.
Yes.
Yeah.
Maybe it's good to. Camera is there.
Yes. First of all, Mr. François, I expected that you were going to come today, so I wanted your signature for the book that you have written before. I brought it with me when I saw your name. But yeah, it's a failure. I don't know how we're going to fix this. The second point, I saw one of the configurations you have been using, because I own the LP600 and the 23 micrometer slit, along with the calibrator and the guided. So the thing is, I saw that one of the equipments you have been using was the amateur 8-inch RC, and I'm still learning. I'm still at the beginning. I'm going to be learning slowly, but I'm taking my very slow, steep learning curve. So can you please advise what are the things that can be done from different stages, from the starting to the beginning, about the simple stuff to be done at the beginning to the most extreme stuff that can be done with the extremely small telescopes, because obviously I'm not going to have any large telescope anytime soon. Thank you.
For me, the advice is that I can give you is this is exactly what you are saying. Go step by step, and don't try to make everything working at the first time. It will not work, or if it works, this is just because you are very lucky and you'll not be able to do it again tomorrow. So go step by step, and when going step by step means first do consider that your spectroscope and your telescope are two different instruments. So control the telescope on one side, control the spectroscope on the other side. And you can use your spectroscope on a bench, on a table, and in cool conditions, in great conditions. And you can use any light you have, including the sunlight, to do your first test and to check how to take spectra, how to process the data, and so on. This is really start by controlling each element separately. Then for me, another important point is that start with a small instrument and start with bright stars. Okay, even if your target is, if your goal is to observe the Doppler shift of faint galaxies, don't do that the first time. Start with the Vega, with the Arcturus, with the Sirius, and really start with the easy stars. And then step by step, you will see that the problems are coming. For instance, if you are observing a bright star, if the focus is not good, if the tracking is not good, we don't really care. And then you'll have to start like that. And I think that's it. And well, my experience says that when we are doing astronomy like that, when we are doing astrophysics, everything is simple. There is no complex operation. We are not doing quantum mechanics. There are only simple things. The only point is that we have a lot of things to put under control. So go step by step, put everything under control, take the time to understand every step, and then when you will assemble the whole system, it will work fine. And if you have a problem, you'll immediately be able to know why is the problem. You know.
Merci. Thank you.
Yeah, just one question for me.
Okay.
Just one question for me, François. So in the same direction that Merlin was asking about what we can do with low resolution. So I saw your comparison between low and high resolution. So for me, I used to say 10,000 is low resolution, but okay, so I understand. So in kind of observing object, so have you already tried to observe a bright comet with this spatial? Or what kind of magnitude that we can have a spectrum of, for example, a comet or even an asteroid?
Well, you know, I am not an intense observer, so I don't have as much practical experience in observation as a lot of people. So maybe I'm not the right guy to give you the right answer. Anyway, what I can tell you that for me, with the 20-centimeter telescopes, which is the kind of telescope I do have at home, and with the Lares-3, for instance, I know that I can go. This is quite feasible to go up to magnitude 7. And if I'm doing a lot of efforts, so if I really concentrate, if I make sure that the instrument is really properly tuned, I'm observing in a good night and so on, maybe I can go to the magnitude 9. You know, so this gives an idea. Now, if I take my LP, which is the low resolution, in this case, I can go down to magnitude 15, maybe. But what is very important is really when you are, you know, the magnitude scale is not the magnitude scale is not linear, of course, and going to 2 more magnitudes is really a challenge each time. And when you go with the magnitude, everything becomes more complex, more difficult. And you have really to take care of everything to be sure that you are not losing photons. And you have to observe for a much longer time, of course. Now, I don't have, I'm sure that with your telescope at UK Medan, with the E-shell spectroscope, I'm sure that on bright comets, you can get them. Now, up to which magnitude I wouldn't be able to tell you, but maybe you have more experience than I do.
Avec l'E-shell, on peut jusqu'à 9 avec la résolution 12 000, avec le 1016.
Yeah, but for comet is quite different because they're extended objects, so they're not stars. So well, maybe we need more. So we need to more bright than 7, I think, because when you're using a slit, so you're not taking all the light coming from the comet, just the part of it, and not sure if we get something with 9. I think this is what my question. I want to optimize at some point if we got some bright comets in the north hemisphere, maybe we can try to go to low resolution spectrum of a comet. But of course, I used to apply for time with high resolution and large telescopes. I'm just wondering what we can do in case of.
Okay, so only what I can tell you is that the observation will not depend on the object that you're observing. Observing a comet from a technical standpoint, from the optic standpoint, observing a comet is exactly the same thing as observing a star. So the tracking will not be the same and so on. But again, all the light, the spectroscope does not know where the light comes from. What it knows is that it is dispersing the light that is going into the slit.
Yeah, thank you.
Okay.
Okay, so let's have a break. About 10 minutes, it's okay?
Okay.
Thank you very much.
Okay.
Thank you.
Can I ask you two things? One, what is the password?